All right, so very last topic in Math 116 is something called the difference quotient. And so in Math 150, so what we're hoping that we all take in the spring, we're going to learn about slopes of functions, all right? So let's just do a little bit of conceptual practice, because when we get to calculus, it is going to be about the algebra, but it's also so much about the concepts and understanding the story behind it, okay? So let's start with this. Whoops, let's start with this. How would you describe the slope?
It's linear.
It is a linear function, but how would you describe the slope?
Increasing.
Okay, it is increasing. What does that mean? Like, what kind of slope does it have? Like, tell me about the slope.
Yeah,
the slope
positive.
is positive, right? So we could say that the slope is positive here. That would be accurate. All right. What about if we had something like this? Tell me about the slope. Good. Okay, so in particular, this slope is 0. Okay. Tell me about the slope of this line. Yeah, we could say that m is negative. Okay. Let's bring back one of our good old friends, the parabola. All right. Tell me about the slope of the parabola. All right, tell me a little bit more. How come it's all three? Like, is it all three at the same time? Like, what's happening here?
Starting from the left, it's decreasing, so it's a negative slope, and then whenever it hits the vertex, it'll be 0, and then going up, it's positive slope.
Okay, so if we were to use a little color coding here, maybe we say positive slope is green. Maybe if it's has a slope of 0, it's yellow. And if it has a negative slope, we'll say that that's red. And yeah, I would agree that like in this one function, there's 3 different kinds of slopes happening. Like the slope is negative, and then the slope is 0, and the slope is positive. So it's not like all 3 are happening at the same time, but at different parts, it might be slope is negative, and then 0, and then positive again. Okay. Let's do one more example, something that we've seen. So we have, what function is this? That is not the square root function. I got an arrow on both ends, so it can't be the square root function. Yeah, this one is going to be a log graph, okay? So I know these are all like little things that we've learned, but really what we're doing is saying all of these little skills, the more we can count on them, like, oh, I know what this is, the more accessible a lot of the other content we're going to learn in the future is going to be. All right, so this is a log function. Tell me about the slope.
I mean, the slope would be positive, but there's also a point where it like flattens out.
Okay, so I would say that you are right. The slope is positive, as it gets to the top, it gets less positive, but it never actually flattens out. Okay, so it never actually gets to a slope of 0. It just gets it's still positive, but it just gets less and less positive over time. Okay. I hope that's not your experience with math, that it starts out really positive and gets less and less positive as time goes on. But this graph, if we think about just the slope of it, it is positive, 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 less positive, less positive, less positive, but it never actually gets to 0. Okay. All right, so we're going to be spending like the first 8 weeks at least in the spring talking about slope. That is a really big theme for us in calculus, okay? And so this last unit is really to think about what kinds of algebraic skills do we need, and so that when we get to the slope section, that we feel ready to do sort of the process. Kind of like if you learned how to multiply numbers really well, then that's something that you don't really have to spend as much brain power on when you need to multiply. You're like, oh, I can just multiply, right? Sort of like a tool that you just have. And so the purpose of this unit or this one lesson is really to kind of just get us exposed to a process that we're going to be learning in the spring, but really thinking about it as a procedure, whereas in the spring, we're going to talk about it as a concept, okay? So the purpose of this is purely procedural, so that when we get to this in the spring, our lives will be a little bit easier, okay? So the directions will look something like this. Use the formal definition of the derivative to find the slope of the function, and you'll have a function here at any point x. And here's what you're going to do. The first thing you're going to write down is you're going to write an LIM. Underneath that, you're going to write h with an arrow to 0. Next to this, you're going to write f of x plus h inside parentheses minus f of x over h. Wait for my, there we go. Okay. So this right here, this whole equation that we've written, this is the formal definition. Okay. That is the formal definition. Now, let me ask you something. If I plug in 0 for h right now, what happens to my fraction? Yeah, if we just plug in 0, we'll get f of x plus 0 minus f of 0 or f of x over 0. And when we divide by 0, that's a problem. Okay. So because we can't just plug in 0, we're going to do some algebra, and then at the end, we're going to plug in 0. Okay. So here's what we're going to do. We're going to write that limit part, and we're going to unpack this piece by piece. So f of x plus h is going to be in this sort of gray color. F of x will be in this yellowish color. And then we're going to have our h still on the bottom. Okay. Now, I claim that you already know what f of x is, right? If you go back to the question, it tells you what f of x is. Now, let me ask you, not what the answer is, but how would you find f of 1? Like, tell me what you would do. What process would you do?
I would substitute 1 in each x.
You would substitute 1 in every x. Perfect. Okay. what if I asked you to do this, f of a?
Substitute A in each x.
Okay. What if I said a plus 1?
Substitute that in each x.
Yeah, everywhere you see an x, you're going to put in a plus 1, right? So it turns out when we say f of x plus h, that means you're going to go to every single x and you're going to put in x plus h. Okay. So here's what this looks like. Let's draw our fraction line. And I'm going to take this yellow equation. Everywhere I see an x, I'm going to put x plus h. So I'm going to have 3x plus h squared, because it's not 3x squared, it's 3x plus h squared, minus x plus h, because it's not minus x, but it's minus x plus h, and then plus 4. And so this is what we have for our f of x plus h. Minus f of x, I get to write just the thing in the yellow. And what goes on the bottom?
It would be x plus h.
No, sir.
Just h.
Yeah, it would just be h, right? Our original denominator was h. So that just gets to stay. Okay. The bottom is going to stay, but the top is really where we're just going to be plugging in things. All right, now we need to do some distribution, some simplifying with our numerator, and let's see what happens. So I'm going to go ahead and put the h on the bottom here because I know I don't have to do anything with that. All right. Here would be my recommendation, okay? With this x plus h, when I square it, if you were someone who forgets to distribute, I might just take the extra step to write x plus h times x plus h. Because the one thing we do not want to do is say x plus h squared equals x squared plus h squared. Right, so that's a really good example of when sometimes if our foundational algebra, we rush through things and we make those mistakes, it's now inside of a much bigger problem, which is going to cause us a lot more problems if we make those mistakes in this kind of problem. Okay, so we want to be really aware of things, these little, like, where do we tend to make those mistakes? All right. So minus x plus h plus 4. So all of this is still that like light gray blue situation. And what can I do to sort of clean up this second part right here?
Distribute the negative sign.
Perfect. Right? That's another huge place, really, really common place to say, oops, I just forgot, right? So minus 3x squared plus x minus 4. And all of this comes from the yellow part. All right. So we're going to distribute here x squared, x plus h, h squared. And we'll get 3x squared plus 6xh plus 3h squared. Now let's distribute this minus sign here. So negative x, negative h. And then that part from the plus 4, and then minus 3x squared plus x minus 4. All over h. All right, so we made it messier, but now it's about to get a whole lot better. What are some things that go away?
The 3x squared and then the negative 3x squared.
Mhm. All right, let's keep that list going. What else goes away?
The 4 and negative 4.
Yep, 4 and negative 4. What else, folks?
The x or negative x and then plus.
Perfect. Anything else? Let's see, the 3x squared, the x, and the h. I think that's it. So let's see what we have left. 6xh plus 3h squared minus h. All right. Remember when earlier I was like, well, what happens if we plug in 0 for h, and we plugged in 0 for h, and it was a problem because we got 0 in the denominator? We're almost at a place where we've made it not a problem anymore. What can I factor out of the numerator?
H.
Yeah. So I factor out an h, I get 6x plus 3h over h. What super common mistake did I just make?
You didn't put a negative 1.
Right? I have a negative h. If I factor that out, I still have a negative 1. Like I need to leave a place for it to go back to if I wanted to distribute it back in, right? Okay, now check this out. H divided by h is 1. And so we get the limit as h approaches 0 of 6x plus 3h minus 1. Now plug in 0 everywhere you see an h. What do you get?
You get 6x plus or negative minus 1.
There you go. All right, my friends. In this problem, we have just used the formal definition of the derivative to find the slope of the function. Okay. You don't have to understand what it means now. That's what we're going to do together in the spring. But this process, we can see we can do the process even if we're not even in calculus yet. We can do the process because we know how to substitute things in. We know how to FOIL. We know how to distribute negative signs. We know how to cancel things out that like add to 0. We know how to factor things out. We know that something divided by itself is 1, so we can reduce that. And we know how to plug in 0 for a number or for a letter. Okay. Very classic kind of situation where, yes, technically this is calculus, but the process underneath it is all the algebra that we already know. Okay. And so what we're going to do for the last bit of class is we're going to go ahead and we're going to practice a bunch. Okay. So we're going to do one together here. Let's see what we have. Okay. All right. So let's do this one right here. All right, so example 1, we have f of x equals 2x plus 5. Now, let me ask you a question, because again, I think this is one you already know the answer to. Tell me about the slope of this function. Okay, I agree. Can you be more specific? Good. So the slope is 2, right? Slope is 2. Okay, so let's apply this formal definition of the derivative to this question, and let's see what we get at the end. So the limit as h approaches 0 of f of x plus h minus f of x all over h. I'm going to color this one that light gray blue situation, and I'm going to color this one yellow so I know where I'm plugging things in. All right. When I plug x plus h into this given function, what do I get?
2 times x plus h plus 5.
Good. I heard parentheses in the way that you said that, and I just want to make it really clear to everyone else that every time we substitute in an x plus h, we should have those parentheses there, okay? So this corresponds to that part. And minus 2x plus 5 is the yellow part. The bottom is just going to be h, so I don't have to do anything with that. All right. What do I get when I clean up that blue term there?
Uh, 2x plus 2h plus 5.
And then for the yellow part?
Negative 2x minus 5.
Perfect. All right. So we did some distribution. All right. Let's see. I see a 2x and a negative 2x. That adds to 0. I see a 5 and a negative 5. That adds to 0. So I'm left with 2h over h, which h over h reduces to 1. And so I'm left with the limit as h approaches 0 of 2. When I plug in 0 for h, what do I get?
Two.
Yeah, I know that seems like a weird question, right? Because there's no h's. But if we think about like, where would we plug in the 0, then the answer is nowhere. We would plug it in nowhere because there's no h's. So that means we only have a 2. Now at the beginning of this problem, I said, hey, tell me about the slope of this, right? It's a line. I know you know the slope. I know you know the slope is 2. But when we did this formal definition of the derivative, we also ended up with 2. Okay, that is not a coincidence. In fact, I argue that if you had a function like this, and you did the formal definition of the derivative, what would you get as your answer?
-1/17.
Yeah. You would get the slope of that line. Perfect, exactly, Matt. Yeah, and that's something that like when we get into the thick of the calculus, if you ever see a linear function and you know that slope is always the same, you don't have to do all of this because you can say, hey, I just know the slope is 2. Or, hey, I know the slope is -1/17. Okay. Where it gets a little trickier is, and let me scroll back up for a moment, it gets a little trickier when we're looking at nonlinear functions, functions that change their slope, right? And so when we described the parabola slope, it was like negative slope, 0, and then positive slope, right? That's like 3 different kinds of slope. Or when we looked at the natural log function, they was positive, but it was all different depending on where you were at. Excuse me. So that's why we're going to focus mostly on ones that kind of look like this, like a quadratic one, just so we can really get this technique down. Okay. All right. So the limit as h approaches 0 of f of x plus h minus f of x over h. That is our formal definition. We've got our f of x at the back end, but we start the numerator with the f of x plus h. So what I'd like you folks to do is this. I'd like you to, I know this is like a lot of typing out, but in the chat, I'd like you to type out what f of x plus h is and send it to me in a direct message, okay? So go ahead and find f of x plus h, all right, for this f of x, this function. See what you get, type that into the chat, all right? So we'll take a few moments just to find the f of x plus h.
Oh, sorry.
You're ruining the surprise for everyone here. Just kidding. All right, so let's make sure that we're getting something similar here, right? Whether you choose to go ahead and write it as negative x plus h times x plus h like Dallas did, or you can write it as negative x plus h squared like some of you are sending over, that is absolutely fine, okay? So either way, at some stage, it'll be nice to see those as sort of x plus h times x plus h, and then minus x plus h plus 3, right? That is sort of the hard part of this question, the challenging part. And then minus the function that we're given, negative x squared minus x plus 3. Okay. Now I would say what makes this particular question a little bit trickier than the first one we saw is there's a lot of negative signs, right? So I get a lot of students who are like, do I have to write all of this out? And I'm going to be that person who says, yes, you have to write this all out. Okay. Being able to see the process here of how you get from one line to the other is really important to me. But I also think that it leads to fewer mistakes as you're trying to like expand things. Okay. All right. So let's see, negative x squared minus 2xh minus h squared minus x minus h plus 3 plus x squared minus x plus 3 over h. So I've distributed, I've expanded, I've thought about those negative signs and distributed them. All right, and I start to think about what goes away. Because at some point, things like a lot of terms should go away, right? So in particular, I noticed that this negative x squared and the positive x squared, that goes away. Does anything else go away?
No.
No, okay. So then we get negative 2xh minus h squared minus x minus h plus, well, I guess I could combine some things. 3 minus x plus 3 over h, which is negative 2xh minus h squared minus 2x minus h plus 6 over h. All right, so remember when we're doing these questions, at some point, a bunch of stuff should cancel out, okay? And more significantly than that, let me go back up to the first problem we did real quick, okay? So when we did this problem, we were able to cancel out a lot of things in the numerator. And then what was magical about what was left is every single term had an H, right? Every single term had an H. That meant we could factor out that H and then reduce it with the numerator. That's actually a sign that you're doing something correctly, all right? That once you get to here, if everything has an H, you're good to go, okay? So how come I still have a bunch of terms that don't have H's, right? I got all the way down to here and I'm like, oh shoot, this is not looking good. Let's backtrack, right? I distributed all my signs here. I distributed my signs here. Negative x squared is a plus x squared. But you know what? Negative x is also a plus x. And negative plus 3 is going to be a minus x. Right? So even though I did all this work and I was like, oh, crap, I'm not going to get everything with an H. If that happens to you, you probably just didn't distribute correctly, just like I did, right? See how easy that was? Like, I'm going along with this. You're just writing things down. We're all just kind of working through it together. It's so easy to make that sign mistake, right? So if you realize that the H's are not factorable, go back up to that really messy line. I bet there's just a sign mistake somewhere, because now we have negative H and positive, or negative X and positive X, and a positive 3 and a negative 3. Now we have a bunch more things canceling out. And in fact, in the numerator, oops, I just have this, right? So it's not the end of the world to make the sign mistake, but it is on you to check for that, right? So now let's look at this numerator. We've got every single term has an H, so I can factor that out. I get negative 2x minus H minus 1. Now I can reduce, and I get the limit as H approaches 0 of negative 2x minus h minus 1. And when I substitute in 0 for h, I get negative 2x minus 1. All right. Now, again, in the spring, we'll talk about why this is the equation for the slope, or what we call the derivative. Okay. But what I want us to focus on right now is, can we accurately work through this algebra independently? Okay. All right. So